Nehu, Shillong. His area of research is in the domain of optical communication, optical amplifiers, especially erbium doped fiber amplifier, silicon photonics, and photonic integrated circuits. Before joining Nehu in 2010, Dr. Arya acquired teaching experience at IIT ISM Dhanbad during the years 2007 to 2010. Professor Arya has successfully produced PhDs in the area of advanced optical modulation formats, plasmonic material-based optical modulators, and multi-care erbium doped fiber amplifiers. He has completed on DST SERB funded projects under the Fast Track Young Scientist Scheme on silicon-based optical modulator for high-speed optical communication systems. He has total of 82 publications in various categories such as SCI Index journals, referred national and international conference proceedings, book chapters, and edited one book also. Dr. Swarnajyoti Patra is an assistant professor in the Department of Computer Science and Engineering, Tezpur University since 2013. He received his PhD from Jadavpur University, Kolkata in the year 2009. During 2009 to 2012, he was a postdoctoral researcher with the Department of Information Engineering and Computer Science, University of Trento, Italy. Dr. Patra, as a referee for the IEEE transactions on geoscience and remote sensing, IEEE pattern recognition letters. His research interests include pattern recognition, evolutionary computation, neural networks, and remote sensing, image analysis. So I would like to hand over the rest of the session to you both. Thank you.
Thank you so much for nice introduction. First of all, very good afternoon. I understand after very much comprehensive lecture given by Professor Swarnajyoti Patra sir, you must have enriched, you must have enlightened. Now this is the contributory article or contributory paper presentation session where about 9 presenters are here. The list which I have given. So there are 9 papers. So I hope that momentum of learning, because sir has already elaborated this active learning. So I think still our participants are in learning mode. They have still retained enthusiasm, and some scholars which are from our Nehu, as well as I can see from NIT Meghalaya, then from Tripura and Jadavpur. So quite wide representation is there. So hopefully with me you will also enjoy their presentation. You will take active part and give proper attention. So with this, I would like to hand over to Patra sir. He would like to initiate something. Yeah. Over to you.
Okay, so we can start now, no? I think. So the first paper ID is 29. Title of this paper is Testing a 6-axis force torque tactile sensor for robotic arm. So paper ID 29.
Yeah, and presenter is Marut Dev Sharma. So presenter has to be given, I think, about 10 minutes for presentation and 5 minutes for interaction. So Marut, you have 10 minutes for presentation. Be brief, comprehensive, and effective. Best wishes.
So, very warm welcome and good afternoon to all of you. I am Arya, research scholar from Department of Electronics and Communication Engineering from NEU. And from 2019, my area of interest is implementing artificial intelligence in robotic arms. So, this is my topic: testing a 6-axis force curve tactile sensor for the robotic arm. I would like to quote one more thing, that all of my these research experiments in this paper, they have been conducted at Russia during a 3-month internship program on collaborative robotics. Right. Rigorously, I worked on UR5 robot, FT40 torque sensors, KUKA robot, like that. So I would like to start with a simple story. When I was a kid, right, my mother used to give me a porridge. Right, I don't know how to eat. I was only 1.5 years old. Right, so what I used to do, I used to take a spoon like this, and sometimes I'm pouring it over my body. Sometimes I'm hitting over my gums like that. Right, so after that, now, what happened to me? What happened to me? The thing is that during the training and learning process, in my mind, I have developed the intelligence. Right? So, whenever I am talking about this tactile sensor, it's a sort of touch sensors. Right? So, in various robotic functions, including the pick and place robot and surgical robotics using haptical approach, there is a need to calculate the forces and torques towards the robotic arm and the end effector too, right? Because in surgical robotics, always force feedback system is needed, right? So in this paper, I have used this mini FT40 torque sensor, and I have tested this sensor by considering one finger at a time, right? One finger, the index one, then the middle one, then the ring, like that. Okay, and maybe at one point of time, because of the time constraint, I have not included all my 5 fingers, including the thumbs also. Right? So, impressing the flows of 5 fingers simultaneously, and I have also given a review why I am choosing this specific sensor for this system. So, what is the real-time problem? The real-time problem is that our robotic system must be an intelligent one, right? If I am grasping some object, it should not be like that it's going to slip down, or it should not be too hard or too harsh, right? So if it is pushing too hard or too hard, it is barely, or I am barely touching it. So it's very difficult. Fine. So to safeguard the robotic arm and the end effector tool from damage due to deficient force feedback system, that's why I am implementing that force torque based tactile sensor into it. And this sensor is basically integrated into the end effector, right? This is my robotic arm. The end effector is this one, right? So I have implemented. Maybe the sensors can be hard, maybe the sensors can be soft, depending on the requirement. Right? So I have used a tactile sensor. Tactile sensor is a sort of touch sensor, right? What do you mean by touch sensor? Whenever I am touching something, right? I want to, from the touch, I am able to predict about the geometry, the system, the material. The first task. The second task is that if I want to pick this object, right? So I will have to calculate the force requirement, the weight, the topology of the system. So this mini FT40 sensor basically uses a capacitive touch sensing. Whenever you are touching the sensor, the finger is having its capacitance, This sensor is having some sort of capacitance, yes, and you can calculate like that. Operation is very simple. If you are not touching, no contact is there, then there is no flow of current. If you are touching it, you are just changing some configurations into it, and some flow of current is there. Like that. This is the capacitance, epsilon A by D. Without touching, it is C naught, but whenever you are touching, you are just changing the configuration of your system, and it is C naught parallel with CD, and you can club it together. Another one is resistor sensor. I have incorporated it, but I have never used it. The material is used is PVDF2, polyvinyl chloride. Right? This is without object. This is with object. Now they are using some conductor rubber because whenever I am going for robotic surgery, the sensor system should be somewhat flexible, right? Because it may hold the nerves or the body part very delicately. So some sort of conducting rubbers are also used. So these are the electrodes. Whenever the force is applied, the rubber is compressed and there is a change in the resistance of the system. This sensor I have used. This is the interface. It's a 6-axis. I can show it over here. This is x-axis. Fx is the force on x-axis. Px is the torque correspondingly. This is F by P by force and torque on the y-axis. And Fz, Tz, the force and torque on the z-axis. Right? Now the question arises because in some review comment they are asking at least you should mention why you are incorporating this sensor into your paper. So first of all, it's a digital sensor because it is new technology, right? So no additional component is needed, no extra circuitry is needed, no signal conditioning, no amplifier, nothing is there. Everything is inbuilt into that sensor, right? So with new technology and innovation, digital sensor can operate, and the important point is that it can operate the extreme temperature and environments. Environment, if you talk in terms of EMI, electromagnetic interference, immediately. If the sensor is put into some interfield, maybe it's a sort of malfunctioning of your sensor, right? But it is unaffected by it. So the next advantage is EMI immunity, no induced or parasitic load from the cables. There is no loading effects, right? Automatically, it is going to nullify by means of some sort of compensation techniques. And quick integration time. It means
Marut, you have please show your results here because time already is over.
okay, sir.
You have only 2 minutes more.
Okay, I will go with first. So, quick integration time, lower complexity, less expensive, noise level low, ready to use data. No need to any interpolate the data, low drift. You are giving input, but you are not getting any output. It is not drift, so no drift is there in that. Yeah, I'm coming to my point. My job. The hardware component that I use is this sensor, right? It is from India, USA. This sensor is plugged with this NAT box with RJ45 cables and some workspace is there. The software component, because in order to communicate with the sensor, the software components are needed. I have worked on ROS, and the version was ROS Melodic Marina, right? Because at that point of time in 2019, that ROS was not integrated with Windows, so the ROS is integrated with Ubuntu. There are some demo softwares and .NET framework. And SolidWorks I have used for the design of the adapter of my system. Now, the point of interest, experimental setup, right? This was NetFT controller box, right? See this one, it is interface M12 cable through RJ45 ports. This is a supply, right? From here it is connected, and this is earthing connection, right? In order to avoid that EMI effect. And this is connected to this UR5 robot at the end effector place. So should I take this one?
You go ahead. Please show your results now, where you have measured your force and torque. No? And how
Some
much
settings
time.
are there in that box, right? The settings are that I only use one setting. This DIP switch 9, it must be on to have a static IP, right? And that 7 and 8 DIP switches, they are used for the baud rate connections, right? If it's 7, 8, 7 off, 8 off, then it is 1 to 5 kbps communication between the NAT box and the server. This is the first. The top cover, these are the status LEDs. This is a CAN bus termination jumper. Some termination is needed because if the signal is moving from one part to another part, it may not bounce back. So some sort of termination is needed into it. And last view, you can see these are the DIP boxes. These are the adapters we have designed because URFan no-board they don't have a sort of adapter to accommodate this sensor. So all this design D1, D2, D3, D5, we worked over it and we have designed the adapter. First of all, the adapter is put into that arm. After that, it is put up and then FD40 sensor it is plugged into it. This is the combined assembly. All have been designed in the solid blocks. Now some network connections. This PC must have a static IP of class C 192.168.1.100 because the default IP of my NetFP is 192.168.1.1. So it should be, in order to communicate, it must be on the same subnet mask. Right? So this one, now connecting RJ45 to M12 and this one, the command prompt you will have to type first ARP-B address it's a sort of address resolution protocol. There are some resolver cache. So in order to bind your IP address with the MAC address of your NetFP, you will have to first of all delete the cache or sort of flush the cache. Some software installation, because there is a software from AT and FT, so you will have to go for some calibration field 16 FT 000 because this sensor can operate under some operating conditions, some range of force and torques like this, and weak monitoring enabled, static IP enabled, Ethernet IP protocol.
Marut, we can understand you have worked, so you love to share those knowledge, but we are interested here to see the results. Since time is lacking, there are more presenters here.
Now, this is the interface, how you can connect from your PC.
All those things are required to get the result. Please optimize your time. You already, crossed your time.
Okay, sir.
Please.
Sir, 192.168.1.1 of that you will have to put. After that, this is called 2.5D visualization of FT sensor console. Sir, this is experimental, right? Are you able to see over there FX, FY, FZ, TX, TY, TZ, right? And this is a solid box. If you are hovering the mask over this tube, it is being rotated. This is x-axis, y, z-axis. If you see this top, this is TZ. It is somewhat green, and you can see the top over here. If you are pressing the sensor, the top by the slider is moving like this. These are the units: force unit, top units, configuration index. It is related to the calibration of my sensor, right? And one more thing, collect streaming. From here you can collect the bottom side. This is the sample observation in my CSV file, separate value file. As you are able to see, this is fx, fy, fz, tx, ty, tz, like this. Now, the data from the index finger. RTT sample rate 500, 500, 500 samples. They are making a column 500, 10,000, then 1,500, so on. Force in unit, the torque is in millimeter. These are the observations.
Marut, you are using this FT40. In the market, there are FT60, FT120 also available. And this is developed by commercial company called ATI. which you have shown you. So whatever design you are showing, that is for your understanding purpose. Don't claim that you have designed. Design is already available on the website of this, ETI company. They have given. So in order to understand, very much you should learn, but don't claim that you have designed that circuit, because it is already commercial a product which they used to sell. You have characterized, you have assessed the its force and torque which you are writing in your article. So show those results. Others are methodology, how to connect with computer, then how to handshake, how to interface those things. Then after taking the reading, you show the results, and it's significant. Now we are not, yeah.
So this is the argument of index finger, right? This is a sequence, RTD sequence in lots of 500, 100. These are the force and torque. Are you able to see from here the torque Tx T by Tz? It is approximately equal to 0. Because the sensor is over here and I'm just forcing like this, right? As per DH convention, right? The z-axis must be normal to the surface. So that's why, sir, we see this FZ is yellow. FZ is yellow, it has got the highest value. FZ is got the highest value. This is for index finger. This one is for the middle finger. Middle finger is more higher, sir. I will go for that, sir. See, this one, FZ, the green one, it is more higher. The data for the ring finger, it is intermediate. See this one, that yellow one. See it? It is in between this and this. Now resultant discussions. Ross one. Every command it is being fired on that Ubuntu terminal. So I will start from ROS 4, right? I have used the ROS distribution melody, and this is the command ROS1 netft util. And see in the starting, this is the original command from netft utils, and I have downloaded it from the kit. There are some sort of repositories posted by that netft. So are you able to see this one? Wrench is a combined term which is used for force and torque. If they are cumulatively connected together, it is wrench. Initially it is 0. X, force on X, Y and Z is 0. The torque on X, Y, Z is 0. But now see, it's a screenshot. Now you are able to see the force on X, Y and Z axis are there when you are implementing it. There are some listening services on the Python by means of running that services, right? So you will have to sort of see listening force and torque of netft 40 sensors, right? So by means of implementing Python code, you can get sort of listening services. So these are the set of commands.
Please maintain time. Learn how to present effectively in minimum time or allotted time.
These are the commands you need to fire in the sequence in order to trigger it. First of all, set up a new workspace. That workspace is known as canteen workspace. Under this, all your netft files are stored, and then you will have to download the package from Git. You will have to clone the package, right? You will have to source the file. You will have to build the package canteen_make. Then you will have to check the FT sensor equal.
Conclude. Please conclude now. Last slide. Come on the last slide. Last slide.
Sir, I have more slides.
No. You are already over time.
Okay, sir. The conclusion is that the force axis, this torque sensor is working satisfactorily when we are applying the forces in all the three axes, right? And if there is any offset voltages already present, so there is a bias patch. By means of that, you can nullify it. And if you compare the result of this middle and ring finger value, are you able to see that the ring finger, the middle finger is, if you are making a grip, this middle finger is more strong, and the weakest finger is that pinky finger, the pinky finger. If you want to open, you can open like this. Okay, so The middle finger, fx value is more, fy value is more, fz value is more. Since I am implementing pressure, I am not going for the top, right? That's why Tx, Ty, Tz is 0. And for that, I have taken the reference from this paper, this one, from Algeria science paper. If you are going for grip strength, the contribution of thumb index and middle ring fingers are 17, 31, and 29 respectively. Depending on
already asked them.
applications, surgical robotics, manufacturing process. I will summarize them first. And in the future scope is that
Next is
there is a term that is known as sensor fusion.
35.
We are not using
Dari
our
Lang
data.
as Lindo. No?
We are not using one sensor at a time.
This one, Dari Lang
To
as
calculate
Lindo.
force or vision or some obstacle, right? So we are implementing a technology that is known as sensor fusion. This one, sensor fusion. So sensor fusion can be integrated with IoT glorification. For references, I have some appendix on the diagrams.
Okay,
These are
thank you.
some precautions. The bending radius should not be more. It should not be more than 1 inch. Otherwise, this transducer will be damaged.
Thank you, Marut. Now, session is open for taking 1 or 2 questions quickly. Any questions from Marut on 6-axis? This testing a 6-axis force torque tactile sensor for robotic arms. So he has taken one case, that is FT40, and measure the forces applied through fingers and torque. So let us give thanks and join hand together for appreciating his work. Continue, but minimize the time because it's essential. Now next title of the paper we have, that is paper ID number 35, and title is ASER of dual hope DF relaying systems with coherent modulation scheme and MRC at destination over Fisher-Sneijder F feeding channels, and presenter shall be Dari Langi S. Lindo from Northeastern Hill University, and co-author is Raj Kishore Mudai, Dr. Raj Kishore Mudai. So Dari Langi, please appreciate the time limit so that more interaction can take place. So you go start.
Good afternoon, everyone. We are respected chairperson. Everyone present here. My name is Arya from Department of Electronics and Communication, Nehru. The title of my paper on my topic for today is ASER for dual lock DF system with a coherent modulation scheme and MRC at the destination over the Fisher-Sneijder F failing channel. In today's cellular communication, we have different generations, of which fifth generation is one of the latest, which is only used in few of the countries, not really established everywhere. But the motivation towards this fifth generation is the need for big data for different utilization. Now, for this big data inclusion in the future, we use one type of communication, that is cooperative communication. Cooperative communication, we can say it's basically like using a single antenna. In a very multi-user environment, that single antenna can act as a relay that can be used for this cooperative communication. So cooperative communication, we use an indirect link, which is known as a relay. Now this relay can be of two types, that is a decode and forward relaying system and an amplify and forward relaying system. Decode and forward is when the relay receives the message from the source. It will decode that message, and when it is successful in decoding the message, it will retransmit that message to the destination. Similarly, in amplify and forward, this relaying system, it will receive the message from the source, and that message that is received from the source will be a noisy type of a message, and it will amplify that message. On successful amplification, it will then retransmit that message back to the destination. So to achieve cooperation, why we call it cooperative, to achieve that cooperation, this relay will also act as a source for transmitting that message back to the destination. Now, at the destination, whatever the signals that we have received, they need to be combined, and the technique used here, we use a maximal ratio combining technique, which is the most efficient type of a technique. This, what it does is it adds all the received signal SNR that is being received from all the different parts. Now, in a communication, failing always occurs in any type of communication. So one type in this 5G communication, what happens is because of the high data rate, there's also a very high traffic load in a 5G communication. So one type of broadcasting that we have used out here is a device-to-device broadcasting. In this broadcasting, the received signal, they will experience both fading as well as shadowing effect. Because of this, it comes a concept of what we call as mixed fading models. And one type of a mixed fading model that has been used out here is the Fisher-Syricot distribution. This distribution, it shows an accurate model of both combining the shadow as well as the multipath fading effects. So this multipath fading effect will observe Nakagami M distribution, while the shadowing effect variations will observe an inverse of Nakagami M distribution. Motivation towards this particular topic or work is there have been relevant studies on the Fisher-Syricot fading channel where different parameters have been analyzed, but it is only done in an amplify and forward relaying system. Here, the dual hub DF relaying system under this Syricot fading channel has not been investigated within the past literature, which is why it motivates for the contribution to this work. Now, the system channel, we can see here we have the source, the relay, and the destination. Then a link from the source to the relay as well as from the source to the destination, a direct link has been considered. Another link from the relay to the destination has been considered. This message has been sent in two different time slots. In the first time slot, it is sent from the destination, from the relay to the destination, and in the second time slot, when this relay it successfully decodes the message from the source, it will send that message to the destination. Then again, combining these two, we use MRC technique. Now, considering the links for all of this, like there is a source to the relay, source relay to destination, we consider that we have undergone a model of that has been modeled in the Fisher-Syricot distribution. We take the PDF of this distribution as equation number 1. In this equation, we see the use of a beta function. We have variables like M, which is the fading severity parameter, P, which is the shadowing parameter. Similarly, we have calculated the cumulative distribution density function, which also includes a beta function along with what is called the Gauss hypergeometric function. We then calculate the outage probability, which is the probability of the collected power that goes below the threshold value gamma TH. Then adding this outage probability into our end-to-end SNR, gamma SRD, we get what the end-to-end as a PDF. Now, one of the performance analysis that we have used here is the average symbol error rate, which is given in equation number 5, one of the techniques for the modulation technique, the average symbol error rate ASER. It contains the conditional SER along with gamma T being the total MRC receiver output SNR at the destination, which includes both the SNR from the source to the destination as well as the SNR from the source relay to destination. One technique that we have used here is the moment generating function, given in equation number 6, and adding that moment generating function into our total SNR, we get equation number 7. Now, when we use this fading model, this fading distribution, Fisher's M, adding it into our MGF, we see that we have a function called the major G function that has been used in this equation, that is this G function. Now, for a coherent modulation scheme, this ASER can be defined using the MGF approach, and substituting this MGF value gamma T, we get a closed form expression of the ASR in the form of Z1 plus Z2. Expanding these two equations, we get Z1 to be equation number 11, Z2 to be equation number 12. This is the mathematical formulation of it. Now, when it comes to the results, we've seen here the graph of this ASER versus the average SNR. In this graph, we have various values of M and P as given in the index portion out here. Now, when we give one of the parameters, that is here we have kept, if we look at these first two lines, this one and this one, When we keep one of the parameters, say the sharpening parameter constant, say p equals to 1, and we vary this fading parameter, we can say that for a higher value of fading parameter, we get lower value of ASR. Similarly, and this has been done, we have considered one of the modulation schemes to be BPSK. Now, if we compare it to another modulation scheme, BFSK, we also see that when we keep P constant and we vary M, again for a high value of M, we get a lower value of ASR. Similarly, now when we keep M constant and we vary P, for a lower value of P, that is for a lower value of the Shannon parameter, we get a higher value, a lower value. So from the system, we can see that increasing the fading parameter and decreasing the Shannon parameter, it gives us a better value of ASR, which is we get a minimum error. The average symbol error is minimized at higher value of fading parameter and lower value of Shannon parameter. Again, this graph shows a comparison of both the modulation schemes, where we can see that the lowest value of this ASR is seen to be in BPSK. So we can say that for this fading parameter, for this system, BPSK modulation scheme is better than BFSK for this dual hop DFT system that is subject to the Fisher's-Singapore error.
What is the reason of being better this BPSK compared to BFSK?
So because the symbol error, the average symbol error that we receive in BPSK is pretty much lower than that of BPSK.
What is the reason? Average symbol error rate is the criteria, but what is the reason why BPSK is better? Why BPSK is giving better ASER compared to BFSK, binary phase shifting, frequency shifting? What is the reason behind it?
So out of the modulator, after calculating and then showing.
No, that calculation is mathematical part, but what is the physical reason? That interpretation should develop, no? Which is embedded in your mathematical formula.
So, like from the mathematical formula, we have just considered any modulation scheme.
Exactly, but mathematical formula, mathematical formula embedded your physical phenomena. So, what physical phenomena is going on? So that average SCR in case of BSK is better than BFSK.
That's the physical phenomena. So the conclusion can only be that we have taken the expressions of end-to-end SNR, PDF, CDF for the dual hop. Expressions of SR have also been derived using movement generating function approach. Then MRC technique has been used. These expressions are all being derived in either in incomplete gamma function or in weighted G function. The numerical and the simulated outcomes, they show the correctness of the effect of the various parameters on this MRC receiver. These are the references used for the framework.
Yeah, thank you for completing your presentation timely. That is very good point, and I appreciate. So session is open for question, taking question, interaction with the researcher. Yeah, please. So C has tried to show the results in terms of average symbol error rate, taking to modulation scheme, that is BPSK and FSK, where this, I think you have used this decode and forward type, decode and forward fixed type. Is there any limitation going for adaptive type?
No, sir, I mean, like,
Adaptive, decode and forward.
We can either go for amplifying forward, decode and forward, or adaptive. But here, I specifically used decode and forward.
But that is, there is an adapter type also. There is a fixed type. So you have used, I think, fixed type, not adaptive type. So is there any limitation while carrying forward this research?
No, there's no limitations that we can use. But like for this moment, I've used the fixed type.
Okay. Okay. So if no more question, then we can move to next presenter. So before that, let us give big hand. Clap. Thank you. So next
48.
paper in list we have 48 number, And title of the paper is Modeling and Characterization of Propagation Delay of Negative Capacitance Field Effect Transistors. So you want tea break? Yeah, I think this is timely need. Everyone must be feeling that to have some break. So you can announce.
Now we are proceed to have a tea break. Please go to the next room.
For how many minutes?
For 5 minutes.
So quick break. We will Yeah, I think, yes, Ronak. So the next paper title is Modeling and Characterization of Propagation Delay of Negative Capacitance Field Effect Transistors. And the presenter is here, Ronak Roy with us, and other authors, co-authors of this uh, presented papers are Rahul Kargi, Tuhin, Rajdeep, Anirban, and Alokesh. So they belongs to two different institutions. One is Jadavpur University, another one is Jalpaiguri Government Engineering College, Jalpaiguri. So over to you.
Very good afternoon, dignitaries, officers. A very good afternoon to my esteemed dignitaries, professors, academicians, my dear parents, and all who have assembled in this program, which is organized by International Conference on Data Electronics and Computing at NEBU, Shillong. I would also like to convey special thanks to chairpersons Professor S.C. Arya and Dr. Swarnajyoti Patra. Myself, Prof, I am currently pursuing Masters in Engineering from Jadavpur University. And today I am here to deliver a presentation regarding modeling and characterization of propagation delay of negative capacitance field level transistors. So we are all acquainted with the term Moore's law. Moore's law states that transistors in a dense IC always doubles itself every 2 years. Now, Gordon Moore first made this observation in 1965 and hence the name Moore's law. Now, what does Moore's law implicate? Means, what is the Moore's law interpret at the transistor level? It simply interprets as progressive scaling down of physical dimensions of transistor. So, is there any detrimental side effects because we are scaling down the dimensions? So, what are the side effects? Yeah, there are side effects, and the major one is heat dissipation, primarily due to static power dissipation, static power consumption. So here in this curve, we see an industry trend for microprocessors over the last 32 years. And we can see from 2010 onwards, there has been 20% number of transistors integrated per unit area. But we also need to think about the power dissipation. You can see that after 2010, the power dissipation is also rising. So in 2020, we need to make a compromise between the number of transistors and the power consumption. So the one simple question arises that is this the end of Moore's law? Yes, it is if conventional MOSFET is used as transistors. Now what's wrong with conventional MOSFET? Now one major problem with conventional MOSFET is that subthreshold slope has a lower bound of 60 millivolt per decade ideally for MOSFETs, but it ranges from 80 to 110 millivolt per decade for practical transistors. Here we can see in this figure that if we apply gate voltage below threshold voltage, the drain current still conducts. So, higher the subthreshold slope, more the subthreshold conduction current below the threshold voltage and vice versa. Now, leakage current increases with scaling down, and this implies drastic rise in static power dissipation. And as a result, it is very critical for performance of ICs. Now, these give an idea to impetus, give an impetus to idea of negative capacitance. S. Dutta and S. Salahuddin proposed the idea of negative capacitance in 2008. Now, what is the idea of negative capacitance? So, this is a usual formula of subthreshold slope, where M is the body factor. Now, if we try to make MOSFET to work to obey the Moore's law for the future decades to come, we need to make certain changes in the architecture. One thing we need to do is that we need to make the body factor less than 1. So what we can do is that we can deposit a dielectric with capacitance C over oxide and so the Cox can be replaced by C equivalent. And in order to make C equivalent less than 1, less than 0, we need to make M less than 1. So for this, you can see that we need to make C, which is the new capacitance of the dielectric that we have deposited, to be less than 0 and mod of C to be less than C oxide. So here, as you are intending to imply that C must be less than 0, so the idea of negative capacitance came into picture. Now we need to implement the idea of negative capacitance. For that, a conventional unit cell of a ferritic perovskite crystal with AbO3 formula has been used. So this is a conventional unit cell of ferritic perovskite crystal where we have A cations occupying the corners of the unit cell, we have B cation occupying the body center, and it forms octahedral structure with 6 O anions. Now, since these are ions, so they will exert electric field on the B cation, and here, so this is the line of the ionic displacement of B ion. So the O parallel ions are those ions which are the top and bottom, which lie along the ionic displacement of B ion, and these two, the right and left, are the O perpendicular ions. Now, O parallel ions, this and this, they produce polarizing field, whereas O perpendicular ions produce depolarizing field at B cation. Now, origin of negative capacitance in ferritic materials. The ferritic materials show spontaneous polarization and switching of polarized states due to applied electric field. So we have two stable states, one is up state, one is down polarized state. So if we make a transition, say this is the stable state in an energy landscape diagram of a typical ferroelectric. So if you make a transition from say up state to down state, so we encounter a energy barrier. This energy barrier is responsible for the negative capacitance regime. Now here, just consider this schematic of NCFET. So if we give an incremental change in gate bias, there will be redistribution of polarization charges due to the polarizing field and screening charges across this ferroelectric layer. Now we have a transient response of polarization charge and screening charge across the ferroelectric layer. We can see, and we need to keep in mind is that the orientation of polarization charges is always opposite to the screening charges on the external electrodes. Now we can see just after the application of the gate bias, this polarization charge attain its stable value after settling time Ts, but the screening charge take additional tau SC time to fully screen the polarization charges. So for the tau SC time, sigma minus p will be less than 0, and del Fe, which is the increment, is the change in voltage across this ferroelectric layer, will also be less than 0. And thus we can conclude that this NCFET will exhibit negative capacitance during the transients in gate bias. Now, using Landau-Khalatnikov theory, we can derive the formula for the negative capacitor. Now, having established negative capacitance and how to implement it using ferroelectric, we will now move on to formulate the propagation delay of NCFET. Now, one simple way to obtain propagation delay for NCFET is to use NCFET both as a pull-up and pull-down common network in a simple inverter that we have done here. So, propagation delay of inverter we know is the average of TPHL and TPLH, where TPHL is the propagation delay for high to low transition at the output level, and TPLH is the propagation delay for low to high transition at the output level. And consequently, we have different on resistance. This is the on resistance for low to high transition, and this is the on resistance for high to low transition. And we will also have load capacitance. So using Elmore's delay, we can have propagation delay as 0.69 R into C. This load capacitance can be derived from this capacitance model of the NCFET, and this model accounts all the passive capacitances, including gate capacitance, junction capacitance, drain to ground capacitance, etc. Now here we have simulated NCFET. Here we have used a 0.25 micron technology node and gate oxide thickness of 6 nanometer, and we have used hafnium oxide as a ferroelectric film, and we have used the thickness of the ferroelectric to be 10 nanometer. Now, and the substrate is p-type. Now, based on the simulation, we've obtained different results, and one of this is the charge concentration of NCFET, and we can see that when we move from accumulation to depletion to strong inversion, the electron concentration, which was almost nil at the channel, it gets increased when we move from depletion, and then it reaches its highest position at strong inversion. We have also obtained IV curves for MFS, MFIS incidence, and NMOS. Now the thing is, what is MFS and MFIS incidence? MFS means metal ferritic semiconductor, and MFIS is metal ferritic insulator semiconductor. So this was MFIS structure, and if we just remove this gate oxide, it will be MFS structure. So we have obtained IV curves of MFS, MFIS, incidence, and NMOS for different ferritic thicknesses, which are 10 nanometer. This is for 10 nanometer. This is for 15 nanometer ferritic thickness, and this is for 20 nanometer ferritic thickness. Now we have obtained substressor slope and ion to ion by IF ratio. Now we can see that MFS NC has substressor slope almost closer to 60 millivolt per decade and is far better than NMOS. And also you can see that the ion by IF ratio for MFS NC is of the order 10⁻40, whereas for NMOS it is of the order 10⁻11. And as we previously provided a way how to obtain propagation delay of NC, so here we modeled a 3D NC inverter, and based on that we have different results. So this is you can see this is the transition from low to high, and this is the transition from high to low. Now we have used three different ferritic thicknesses, and yeah, this inverter it is of MFIS incipient inverter, and thicknesses are, this is for 10 nanometer, this is for 20, and this is for 15, and this is for 20 nanometer. Propagation delay of incipient inverters. Now for 10 nanometer we have a delay of 8 nanoseconds, for 15 we have 16 nanoseconds, and for 20 we have 26 nanoseconds. Now we have arrived to a conclusion. So in this paper, we model 3D models of MFIS and MFS incidence with different ferritic thickness, and we saw that MFS incidence shows remarkable results compared to MOSFETs, and the substressor slope of MFS incidence is lower to a great extent compared to MOSFETs, and as well the ion by IF ratio of incidence is also far better than MOSFET. Now from simulation results, MFS NC provides optimum results if we use ferritic thickness to be 20 nanometer. MFIS NC exhibit results close to MOSFET, but if we use ferritic thickness of 10 nanometer, we will get optimum result for MFIS NC. Now with proper capacitance matching using appropriate ferritic material, MFIS NC would also exhibit much better results compared to conventional MOSFET. Now based on the simulation results, we can infer that MFS NC can be a good substitute of MOSFET to obey Moore's law in future decades to come. So these are the references from where I have included information in my presentation. And thank you all for your questions.
Thank you, Ronak, for nice presentation. So session is open for questions. Participants are encouraged to interact with the research scholars. He is very young research scholar, and welcome in domain of research, and you are participating in international conference. We appreciate his gesture and effort. So yeah.
Just one question. What is the specific measure you are taking to reduce the leakage? That is a very...
No, yeah, the thing is we focused on reducing the substressor slope. Because if we reduce the substressor slope more, because we emphasized on that 60 millivolt per decade limit, lower bound. So we need to make the slope lesser than this. If you do so, then the conduction leakage current will be reduced to a great extent. And that's why we have embarked in a journey to go for negative capacitance. Yeah.
Is there any connection with this material based on which you are developing the device?
Yeah.
Is that connected with the leakage current or change paper? Sometimes it happens that...
Yeah, sure. Yeah. It also, yeah, that's why I said that. Yeah, that's why I said that to make capacitance matching, we need need to take different periodic materials, because for periodic materials we have different spontaneous polarization, eminent polarization, and permittivity. So based on this, yeah, it will differ obviously.
Any more question from participants? So one question I would like to ask. You have already done this, full physical modeling using Atlas
Yeah,
and
yeah,
Silva
Silva.
Pro. So 3D. But you are also proposing this compact model of this physical interpretation. So why we go for compact model?
Yeah. We compact model in the sense that we need to compact because we need to compact it with ferritic thickness, because and as a result the MOSFET with just a deposition of the ferritic can be used as a compact one, and it will be used and it can be used for obeying the Moore's law, as you can see by reducing the substance to below 61%.
Okay. Okay. And what and this propagation delay time you are reducing. This is the your
Yeah, we have an analysis, yeah, on the propagation data.
okay. Thank you. So let us give big hand to young researcher, and thank you for taking the expected time only.
Yeah.
Good. So with this we will move to next presenter. The title of paper is Outage Probability of a DF Relay Assisted Communication System over Mixed Nakagami M and Webull Fading Channels. And the presenter is here. Deep Vaishya. Okay. Welcome. So 10 minutes for presentation. Paper ID
49.
is 49. Yeah, fourth paper. Outage probability of a DF relay assisted communication system over mixed Nakagami M and Webull fading channels. Yeah, this is it. Start.
Good afternoon, everyone. My presentation on this topic on outage probability of a recurrent over delay assisted communication system over mixed Nakagami M fading and Webull fading channel. Myself, Kosho, and I pursued my MTech from Nepal, and my co-author is Mr. Muller sir. These were my contents which I have presented before the first abstract introduction. So the related coordinate system model, outage probability, which is the parameter I have been taking on, the results, the conclusion, and that's it. The outage probability has been analyzed for a recurrent forward relay phase, the dual mode wireless transmission technique over mixed Nakagami and the Webull phase. The operating model, considering this paper concept of source DF relay in the destination. It is pretended that the source relay as well as the relay destination suffer Nakagami and Webull channel respectively. The outage probability expression is derived and illustrated is saying that the increment of the filling parameter and the outage performance improves. Similar with the enhancement of the Webull filling parameter, that's taking the second filling parameter, this performance improves. Cooperative communication and networking are one of the new technologies which is the fastest growing in our research. It enables the efficient spectrum users which promising high reliability and spectral efficiency in the wireless network. The main idea of this cooperative communication is the resource sharing multiple nodes in the network. In a wireless communication, when the source and the destination are interconnected by means of node, which means a long range link in a chain of short range link, that node is called a link. Nowadays, the cooperative communication with the assistance of relay that tracks increasing attempts for data performance gain compared to the direct transmission. The two main relay protocols used in cooperative communication are amplify and forward, and
echo and forward relay. In amplified and forward relay programming, that relay amplifies the signal transmitted by the source and retransmit to the destination. And in decode and forward, the relay decodes the signal and transmits by the source and encodes and transmits to the in this way, I have been still decode and forward. The related work that I have gone through. Some of the research that I have been done in the past are from ICDEC, PK Varma, AKC, on the outer mode of multi-hop parallel decode and forward relay in NACA training center. And second one that encompasses and MDE in the paper outer probability analysis of dual hop decode and forward relay over mixed relay and channel schema training center. And another one, 8 Suraya and 2A. And for the paper 2 hop amplify and forward transfer in mixed relay and recent furniture. However, to the base of our knowledge, the outer probability of dual hop VF relay over mixed Nakagami and waveform prediction has not been performed in the application so far. So I have taken these two instances for my work. The system model. Here you can see from the source. From this source to the relay, I've been taking the Nakagami fading here, and from the relay to the destination, I'm taking the wave fading. When there is one second delay, so for this, it dual hop relay system instrument. So, dual hop relay system is known as to enabling the extend coverage and reduce the transmission cost. Here, we have taken Nakagami distribution fading channel because it gives best fit to the LAN mobile and indoor mobile multi-bar propagation. A same as well for the able distribution of the for indoor and outdoor area. So for source to relay, we taken the Nakagami fading. So for that, the CDF of the SMR instantaneous and SMR. This is the question we are taking. And for the relay to destination, for the vehicle fading, the PDF of instantaneous SMR, that is being shown. And the parameter I have taken is the outage probability. So outage probability is the standard performance characters of diversity system operating over fading signal. It is the PR. The outage probability can be defined as a probability that the instantaneous SNR falls below a predetermined threshold. And mathematically, you can see PR probability minimum gamma 1, gamma 2. There are the two variables. Gamma 1 is for the Nakagami and the gamma 2 is for the wave. And this is less than greater than gamma threshold. Same as from simplification of the wave the main equation. That's what we should have.
This you can come on your results. Still these mathematical derivation will come on the results. You describe the results.
Yes, the results are going to. After simplification, where for Nakagami and fading channel, we get the final expression. And for the waveform fading channel, I will get the final expression. So after getting Nakagami and fading channel and then for the waveform fading channel, we go to combine and using the formula that I got for the outage probability. So the final expression is used for the outage probability. After getting the outage probability expression, we have get the result. That the graphs or we have taken for the outage probability versus average SMR, where we have taken threshold SMR for 2 dB and 6 dB. Here you can see here is a straight line, which combined line. Because from as the SNR is low, the noise is more. So if we are failing the amp parameters, if we are failing the threshold SMR, for that low average SMR, that line will be same. So after that increasing the SMR, then the lights disperse, and as you get from here, from this graph, we get that when the outage probability is drop and the average SMR it rises, the performance is getting better. So as compared to the two threshold SNR, we get to know that the 2 dB gets a better one. Same as for the next fading parameter, we have taken same. For we have the fading the C246, and for then only we have taken threshold SNR for 2 dB and 6 dB. Same as here, you can see here that get the same one line. Because that for the SNR is true. Similarly, with comparison to outer flow and average SNR, that the probability is low and the average SNR rises, then we get better performance.
This trend of increasing in average SNR,
Yeah.
probability, outage probability decreases.
Decreases.
That is quite obvious. Okay, it will be in all cases.
Yes.
Okay, so now tell me from this graph,
Yeah.
which for which value of SNR corresponding to the outage probability we are going to recommend for system design.
So for then it will be like such we have to take the parameters equal to 6.
All values you have already shown there.
Yes, sir.
For system design engineer, suppose a communication system design engineer is in front of you. You have from this graph, tell me for which value of average SNR and hence outage probability you are going to recommend. One has to design the system. No?
So it will be the same that
What is the ultimate conclusion? Because this trend of curve is implemented or applicable for all kind of communication system. You increase the SNR, outage probability will be decreased. Means increasing the SNR means increasing the value of signal, reducing the noise. That is the increase in SNR. And of course, then error will be less. Okay, so that is quite obvious. But for what is the standard value of SNR for system design?
so it will be 20 dB.
20 means
So
maximum
after
value.
average up to it will be 20 dB, and we have to take sorry, it's for experimentally. We will be getting lesser value, we are getting the better one. So for me it will be 2 dB as in shown in the graph. So I
2 dB of what?
so
2
it
dB
will
of SNR or what?
so threshold SNR is it will be the perfect one for me after getting this.
Okay. Next.
In this proposed work, we analyzes the outer of EFA links over mixed and wave fittings. The PDF expression was derived was stability fittings and shows to relate experiencing the underlying and visual fittings. Now, this probability is being derived in terms of gamma function. The simulation results verified and accuracy and correctness of the compositions. That these were the references we are taking.
Okay. Thank you, Deep, for your nice presentation. Session is over. Session is open for questions, taking up the question from the participant. So he's trying to show the one of the important characteristics of communication system, that is the outage probability. So he's trying to characterize the outage probability increasing in the SNR. So anyone? So beside, if no question from the audience, I will ask. Beside this outage probability for communication engineering, what are the other parameters for characterization?
Here is here to put next to the future. I think for the future, that will be the better for me. It is the initial
Average bit error rate or symbol error rate, outage probability, more or less all are linked. Can you think about this eye diagram? Have you heard about eye diagram? Which gives the qualitative representation of system's ability or its level. Error vector magnitude. think about that because I diagram you must have seen will give the bit error rate. So that is so. Try to include those parameters also in your interpretation. Besides the outage probability that is here. Yeah, I forgot to tell the name of co-author is Dr. Raj Kishore Mudai. He is here among us. So, okay, so best wishes from our side to carry forward this work. Okay, so so give a big hand to him. So now next paper title is a triple band reconfigurable filtering antenna with high frequency selectivity. And authors of this article is Sangeeta Das and Dr. Pankaj Sarkar, who are here. So Sangeeta Das shall present this outcome of this result, outcome of this article.
Sir, this one would be online within this session. This one is a medical reason is not able to come.
Okay.
You will have online.
In that order only?
In this
Order only?
not order, not last term.
Okay. So Sangeeta, you will given 10 minutes. Please maintain that time so that we can have discussion on this.
A very good evening to all of you. Myself, Patra, a research scholar from Northeastern University. The title of my paper is Retrieval and Reconfigurable Filtering Antenna with High Frequency. So these are my audience today I am discussing. So let us have a quick look on my abstract part. It's simply presenting a retrieval and reconfigurable filtering antenna. The main novelty is that our structure is very perfect and it is offering both wideband and narrowband application. For that, initially we have designed a wideband filter which composes two types of resonator. The upper half of the filter it constitutes a two uniform impedance resonator which is resonating at frequency 5.45 GHz. The lower half of the filter which constitutes a band tissue resonator which is operating a band which is centered at 2.8 GHz. Here we are using a transmission line just below the feeding line, and the main purpose of the transmission line is to produce additional transmission zero within the desired frequency band of impedance. Here also we are using two non-resonating UIRs introduced in the proposed wideband filter, and these UIRs are designed in such a way that the band from 5.35 to 5.5 GHz we have eliminated just by creating a notch around 5.45 GHz. Finally, next we have designed the broadband antenna next we have designed a broadband antenna which is composed of a ground ring, an inverted L-shaped resonator, and a monopole radiator, and final which is covering the radiating frequency range of 2.6 to 6 GHz. And finally, what we are doing is we are just cascading the filter into the feeding line of the antenna structure, and just by properly biasing the pin tire, we can reconfigure the proposed triple band filtering antenna into different band configurations. So let us come to motivation why reconfigurable filtering antenna is required. Gradually, the demand for the wireless communication system, say your Bluetooth, wireless, Wi-Fi, wireless, etc., the demand has been increased. Therefore, if we see the present trend also, your device is always becoming small, and almost most of the wireless applications are integrating into one devices. Therefore, what is happening? The concept of the multiple antennas has come to the researchers' mind, but there are also some limitations are there, where by using the multiple antennas, the system cost and the space requirement will be increased. To overcome this problem, the use of reconfigurable antenna has the concept has been come, and this reconfigurable antenna uses some sorts of biasing line in the antenna radiating element. The uses of biasing line also creates some problem because it generates some unpleasant resonances in the antenna operating band. Therefore, to overcome this problem also, finally it is highly recommended to the use of reconfigurable filtering antenna, because reconfigurable filtering antenna, as you can see, it is a composite structure of both filter and the antenna structure. Therefore, it has the ability to filtering the unwanted resonances also, and simultaneously it has to provide the radiation characteristic also according to the user's demand. The novelty of the, as I have already mentioned, the novelty of our filtering antenna is that for each lab configuration, it is providing a high selectivity operation, and the whole structure is flexible for wideband and narrowband application at the same time. So this is the layout of the 12 bandpass filter design. Here you can see that two types of resonators we have been used. In the upper half of the field line, there are two uniform impedance resonators, and the lower half of the field line is R2. This is nothing but the band tissue resonator, which is operating at the frequency range centered at 2.8 gigahertz. A transmission line you can see in the middle, just beneath the feeding line, the uses of the transmission line, you can see from the plot that if we are not using the transmission line, the passing performance is very poor. So as you tune in the line from 9 millimeter to 13 millimeter, you can see there are additional transmission zeros forming in between the desired frequency band of interest. So we can conclude that by using this transmission line, it eliminates some unwanted resonances in the operating band of interest, and it also helps to create additional transmission zero, thereby it increases the selectivity of the structure. For simulation, we are using the advanced design Session-2, and the whole structure it is made up on F4 substrate of height 1 millimeter. So this is the even and odd mode analysis for the lower tissue resonator. You can see that two equivalent circuit, even and odd equivalent circuit, you can see in the slide. These frequencies are mainly calculating by putting input admittance y in odd and y in even equal to 0. These frequencies are derived just to know the physical dimension of the length of the resonator. And from the plot also you can see that just by regulating the L5 is that this length, just by regulating the L5, you can shift the both the lower and higher even mode resonances. And this is a composed triple band filtering antenna. Here you can see that another two non-resonating wires have been used, R5 and R6, and these resonators are designed in such a way that it has the ability to eliminate 5.35 to 5.5 gigahertz by creating a notch around 5.45 gigahertz. So there we are using total 4 pin diodes, and these pin diodes are biased by giving a forward bias voltage of 5 volt and show a RC of inductance 2.4 nanohenry. The another terminal of the pin diode is connected to the ground with the help of an inductor. So the working mechanism is that total 4 pin diode, and it is providing total 6 different lab configuration, and corresponding to this it is providing 6 different output characteristics. So when the diode D1 is off and D2 is on, and at the same time D3 and D4 is off, the structure is able to give it different configuration at the output side. Similarly, when the diode D1 is similarly, when the diode D1 is off and D2 is off and D3 and D4 is also off, means all the diodes are off, then the structure is flexible to give only single band configuration, which is giving the lower pulse band. The same time when D1 is on and D2 is on and D3 and D4 also off, at the same time another single band filter can be found at the output side. When the diode D3 and D4 when the diode D3 and D4 is off and D2 is off and D1 also on, you can see that there is no coupling in between the resonator R3 and R4, and the down tissue resonator also, as it is grounded, therefore the frequency also changes, therefore no coupling takes place. Therefore, in this configuration, the structure can be used as a all-stop filter. For the fifth type configuration, when the diode D3 and D4 is on, means when the diode D3 and D4 is on, the resonator R5 and R6 are active. Therefore, as I already told that it is creating a notch around 5.45 gigahertz. Therefore, in this configuration, the structure is able to give a triple band configuration. And for
you are nicking on and off these three diodes, four diodes, four diodes to make it reconfigurable. So, from where you are taking the output? From which port you are taking the output? Which one? So that needs to be written. So these are the output ports. Acha, one more thing. What is your design approach? Since you are using 5.45 frequency and then another also 2.8, then 5.35, etc. So what is your design approach? First you fix the frequency and then accordingly go for the parameters of your design, or you first design your circuit and then find out at which frequency it is going to filter. So what is your approach?
According to the design, we are trying to calculate the physical dimension.
Physical dimension and its topology.
Yes, sir.
So how you have calculated?
We have given an analysis portion, given a compound theory.
Okay.
This is very simple. This calculation of frequency also very simple.
Okay. Why these frequencies are said in points one? Because people need to remember the point number like 5.45. Why not 5 or why not 6 gigahertz? What is the reason? Like here 2.8 gigahertz. Why it should not be 3 gigahertz? Because even designing the circuit will also may be problematic. If we take the round number, it will be easier instead of taking some fractional number. So what is the reason? There must be some reason. I would like to know from you. What is that reason? What is so peculiar in 5.45 gigahertz?
So it may be 5.5 gigahertz also or 5.4 gigahertz also.
Then why not 5 gigahertz? Simply.
According to my physical dimension, whatever dimension I am taking.
But you told that first you have determined the frequency and then you have gone for design parameters.
If I physical approach also, if I design.
Now my question is that why you have chosen 5.45?
Because in my objective also either.
What was the reason of selecting this objective? Why not 5 or 6 gigahertz?
Because this 5.4 is especially for the widen 5.1 to 5.8 gigahertz. So maybe their center frequency is nearly 5.5.
Okay.
Maybe 5.45 also.
Yeah. Okay, continue. Sorry.
So this is the simulation results of the proposed filter. So for the first step configuration, you can see the structure is everything square orbital configuration. If you can see the selectivity is quite satisfactory. For the first person, the density fractional memory is coming around 25%, and for the second upper person, it is coming density fractional memory is around 7.5%. Four transmission zeros is created, and for the second type configuration, you can see when all the lights are off, it is giving output is giving the first person configuration. And in this configuration, the structure is able to give lesson, but is able to give wideband application. And for the third type configuration, another single passband filter is achieved where you can see that the resulting frequency is found at 5.45 gigahertz. And for the fourth type configuration, the structure is can be used as an all-stop filter. And for the fifth type configuration, you can see this 12-band filter now can be tuned to a triple-band filter. Here in this configuration, it is giving both the wideband and the narrowband application at the same time. And for the sixth type configuration, when all the lights are switched to on state, you may see that there are two narrowbands we have achieved. So in this configuration, the structure is able to be narrowband filter. So now our next part is antenna broadband antenna design. I'm going to discuss. Here you can see that this antenna it is mainly composed of a monopole radiator and a ground ring and a L-shaped inverted L-shaped resonator. The design is shown in the figure step by step. First, this monopole radiator it is designed to achieve a radiating band which is around 5.45 gigahertz. Second, what we are doing is we are just enlarging the ground plane in the shape of a ring, and while we are making it in the shape of a ring because the full wavelength resonance of the ring is marched to the fundamental resonance of the monopole radiator, which is giving a broadband characteristic for the as it is shown in antenna second. And finally, to increase the impedance bandwidth, we are using another inverted L-shaped resonator, and now you can see that our bandwidth is increased, and the NDP fractional bandwidth is around 80%. So, thus the proposed antenna can be used as the broadband antenna. So here you can see that surface current distribution for the upper and the lower resonating node. For the upper lower resonating node, you can see that the high surface current is induced in between the monopole radiator intervene, and for the higher resonating node, the high surface current has been induced in between the L-shaped resonator and the monopole radiator. So this is the gain plot under the different frequencies of the with a peak gain of 3.5 dB we have achieved. So this is the radiation pattern for the three resonating nodes. Here you can see that here the structure is offering commutation and radiation characteristics. So finally, what we are doing is we are just simply cascading the filter, proposed triple band reconfigurable filter to the feeding line of the antenna. Here the shell gray one is the bottom layer, which is the ground plane. Here the whole
Sangita,
structure is built.
conclude your presentation.
Here the whole structure is used in for the purpose of EM simulation. We are using CST Micro Studio, and this structure is made up of FIO substrate of height 1 millimeter. And this question I have already, this filter question we have already discussed. So directly come to the output characteristic. Here also this the structure is maintaining 6 different band configuration according to the. You can see configuration 1. The antenna can be used as a 12-band antenna. For configuration 2, and configuration 3, the antenna can be used as an 2 different single radiating band antenna. And for the configuration 4, you can see that the structures can be used to all-stop antenna. For configuration 5, you can see the 12-band antenna now can be tuned to a triple-band antenna. And for configuration 6, the structure is reconfigured to the narrowband antenna. And this is the gain plot of the composite structure, where you can see that total around 6.36 dBi of gain is achieved. So this is the radiation pattern of the proposed configuration for the two plan 520 dB and 590 dB. Here also you can see that omnidirectional radiation pattern characteristic is achieved, and this one is the radiation pattern for the narrowband configuration for the two plan 520 dB and 90 dB. The if we see the gain for all the configuration, you can see that radiation of the gain is very less for all the radiating band. So now let us come to the conclusion. We can conclude that the same structure is now flexible for the different multiple applications. Sometimes it can be used as a triple band, sometimes the single band, and also characteristic and vice versa. The structure is also flexible for wide-band and narrow-band application. And we are using a transmission line just to remove the unwanted frequencies from the desired frequency radiating band of interest, and thereby it is helping to increase the filter structure selectivity. As it is providing the omnidirectional radiation characteristic, obviously it is satisfying the y-mix and y-length band. And if you see the size also, the structure is very complex, 16 to 26 millimeters square. So if we compare the performance parameter of the structure compared to the previously reported structure, the proposed structure has less insertion loss, it has very high return loss, and also upper characteristic, and also it is providing the satisfactory. So these are my references.
Thank you, Sangeeta. So session is open to invite the questions from the participant. Any question? So she has presented this reconfigurable filtering antenna for triple band high frequency. So this is the demand of time that your antenna or filter should be reconfigurable. so that with the lesser circuit complexity, more functionality can be achieved. So thank you for presenting your valuable outcome of research. Thank you so much. So let us give a big hand. So I think we can move to next article. That is title is effect of noise in Hasi speech recognition system. And the authors of article are Feriki Rinja, Khair Cooper, Jindiang, Bronson Siam, and Professor L. Jayaprakash Singh. And presenter we have Feriki Rinja. Now this will be your area. So Feriki, present nicely and please appreciate the time. 10 minutes time. You can conclude. So you will be rewarded 4 marks.
Yes.
Okay.
Good evening, teachers and my friends. The topic of presentation is effect of noise in passive speech recognition. So, just giving the outlines here, which is happening here, we have the introduction, related works, and then some of the basic information about the language, and then the model which we are going to work on this language, the database description which we have collected, and the experimental approach, the results of discussion, conclusion, and reference as we start. So, as per the introduction here, we say here we have, despite we have there has been research for decades on this speech recognition systems. So we still have no system which will recognize the system, the data are correct. There cannot be a system which can be recognized correctly, accurately, which is 100%. So to obtain better performance here, ASR systems must have amount of limited data in presence of noise. So what happens here? We are trying to incorporate noise in our clean data so that we can also try to incorporate, like we can find out the difference. How much noise can be removed from an available data. So we can also have here what we have the additional noise. The addition of noise is clean signals considered normally in real life applications, which we know that it's not possible in any ideal signal or data. So we are developing the system in the open software tool called ASR toolkit. Then we compare here. Why we are taking this particular model here is that we will come later into the last part conclusion. That we compare here with the GMM, the Gaussian mixture model, and we have taken here the subspace Gaussian mixture model, which is one of the efficient ASR frameworks. So it is also very compatible here with the acoustic modeling and the speaker adaptation training. So this model here, it uses 2 parameters. Which are normally tied to the acoustic state and which have several parameters which are shared globally in one total space, so that it can be, we can also consider for any small or limited number or limited amount of data. So next part we have the related works. There has been few of related works which have been done by few of the researchers here, and they have done in different language, in different database, in different type of tools, and they have some of the results by employing this addition of noise. So in this part, the first part here, Patra et al. Has used this 3 features, MFC, PLP, and LPCC, using HTK, hidden toolkit, and using this addition of noise here, they have found that the results that these are the two parameters here, or these are the two features. MFC and PLP, they have given better results with increasing SNR levels. So the second part here, Krishnamurthy, he has done the work on GMM, UM, and has obtained an accuracy as 78.20%. But after adding the noisy data and muted data here, accuracy has of 80% has been achieved. So we can say that adding the increasing the SNR level also it has improved the system accuracy. Then the third one here in the Sama et al. Developed a robust meso-digit cognition system. Here also they have added the additive noise, which they have worked in using the SGMM HMM model, and they found that in any of these models here, it is actually showing better results in the with increasing SNR level. So the other one here also is working on this the baseline here. Okay, these are just these related works. These are the basic facts of the Khasi language. So I'm just taking here, we are taking the focus of the standard Khasi dialect, which is one of the common dialects for communication in Meghalaya. So this is the space Gaussian mixture model. So in here, the speech states the mixture weights, the means, and the covariance are obtained for global shared weight and mean matrix. So it utilizes a low-dimensional specific vector rather than being trained traditionally as a GMM model. So model consists less number of parameters. The model here consists of less parameters compared to a traditional GMM, since the full covariance is accessible among states. So inside that particular state only, the parameters has been shared.
How many parameters are there in normal Gaussian? Normal Gaussian model, how
We
many
are
parameters?
using, for this particular, we have used 400.
No, how many parameters are there in normal Gaussian model? Traditional Gaussian model, how many parameters are there?
Oh, for that, it is around, we're using the number of loops also, which is around 900.
Okay.
It implies that using less amount of data is also possible while developing some parallel models and maintaining system accuracy.
Maybe it's surprising. As a layman.
So this is actually the description of the database here. So these are the features why we have used. This is the process here why we have separated first the 16 kilohertz, and then this is the windowing process with 5 ms, and then the 10 milliseconds frame shift, and this is the single window reduced to 30 frames, which is static features, generating the static features. And then for the second and third order, we have the dynamic features. Total of 39 feature vectors has been static for each frame. Then this has been supplied to a CMVN, that is a central mean variance normalized for using as the training path. So we have used this experimental approach here in the SR toolkit. Initially, we have find out after extracting the features, we have trained the monophone model. Thereafter that, we have considered which is also taken default parameters of Kaldi. From the trained monophone, here the calculation of alignments utterance was done, which were used in Triphone 1. So we have generated the Triphone 1 model from the alignment of the monophone model. Then the delta features are computed in Triphone 1 model. After that, we have reduced the dimensions for 40 for taking the LDA, followed by the alignment of Triphone 1 model. Then, which is actually we have found out the triphone model, which was trained using the SAT algorithm, the speaker adaptation training. The alignments were used for preceding model, that is, we have aligned first before generating the triphone model. So SGMM model was developed on the top of triphone. So initially, before we develop any SGMM, we have initially given into the UBM, that is the universal background model, and then by setting up our Gaussians of 400 here. So in this part here, we have the results and discussion. So noise addition is performed to increase the number of speech features artificially. This additive white noise Gaussian added clean. We have taken the three levels of noise, that's 10 dB, 20, and 30. We observed that features with or without additive noise was carried out with or without speech data here. So we can see here in this next figure. It's too small, actually, the scattering here, the distribution of first trig coefficients, where we can see the top part, the left, is the clean part of here, the clean data. We have taken from there, from 200 milliseconds of one particular speech. If suppose if one data here, one speech data is 1 second, we have taken by only 200 milliseconds. So then the same thing with this also, with the same. Same thing here, we have the 10 dB and the 20 dB and 30 dB noise, and the distribution of first trig coefficients here. The number of frames you have taken here, that's what we have seen the colors here, which is the number of frames, 50 number of frames here. And then the distribution of three coefficients here in feature space after adding the clean plus noise. So in the first part here on the left side, we have the clean plus 10 dB. And then the second part here, we have the clean plus 20 and then the clean plus 30. So if we can observe here from this distribution also that the distribution here and the distribution of this particular is almost as near to this clean. It's almost near to this clean here, and we can also observe from this spectral density also that in the clean data here, it's about the overlapping between the clean plus 30 dB and the clean. So that's why we have, we can see here that there is a variation between clean plus 10 dB and the clean and clean plus 30 dB. So we are not moving ahead here to clean plus 40 because there has been around more than 80 or 90% overlapping. So this is the, based on that, we have taken these tables here, generated using the subspace Gaussian mixture model, and there has been an improvement in the WER here from taking the SGMM here. We got in the NFC is 14.30 and ELP is 14.31. So there is a reason here that is because of the non-linearity of the data here that we are getting more a better performance in MFCC. So this is also here that there's a difference, same difference, there is a huge difference between this particular data here and this clean plus 20, whereas there's almost zero difference between this clean plus 30 and clean. So this is the results here. So
okay, you can finish now.
So when we lower SNL, that means it deteriorates the cognition system here. So our observation is that we have to find out with our own data how it is performing with adding noise by comparing with other with other research works, with other works which has been done in different other databases. So our future work will be if we add some more data, and then we can also explore some other learning methods as the end-to-end systems or other neural networks. Is that a reference?
Thank you, Praniki. So session is open for question, taking up some questions from the participant.
No, if no one has question, just how can you add additive noise?
Pardon?
How can you add noise? 10 dB, 20 dB, how can you add in the data, original data?
No, we actually have generated the noise.
How?
We have incorporated using programming tools,
Using?
using the programming tools in the Python.
Okay. Okay. Thank you.
Okay, thank you, Ranjan. So we will begin. So next presenter will come to present a paper titled on 3D thermal modeling of silicon carbide avalanche transit time oscillator under large signal pulse operating conditions. So, and the authors are here: Nritya Biswas, Devraj Chakrabarti, Madhurima Chattopadhyay, and Mamita Mukherjee. So, who's available here? Uh, Nritya Biswas, is it? Nritya Biswas, no?
Good afternoon.
What is your name?
Okay.
Okay.
Good evening. Good evening, everyone. Myself, Niratya Vishwas, working as assistant professor in Asansol Engineering College in West Bengal, and my co-authors are Devraj Chakraborty and Dr. Madhurima Chattopadhyay and Dr. Mamita Mukherjee. Dr. Madhurima Chattopadhyay and Dr. Mamita Mukherjee is also my PhD guide for enrolling in PhD program in a technical university in West Bengal. So the topics that I am delivering here, that is 3D thermal modeling of silicon carbide based avalanche transit time device under large signal pulsed operating conditions. So basically these works are based on wide band gap semiconductor like silicon carbide, which can deliver high power, that is mainly used for high frequency and basically used for defense application, where we are using above 94 gigahertz to 140 to 20 gigahertz. Okay. So the outline of my work is that objectives, then device physics, then the physics-based thermal modeling, and then results and discussion. So in this type of additive device, the major problem is that majority of the energy that is given bias energy that is converted to heat. So one of the challenging work to how to dissipate the converted heat energy during the pulse on time, since we are working the pulse on mode. So the objective is that to develop 3D thermal model and then study the thermal stability of the device, that is how the junction temperature rises during the pulse on time and how it is extracted when pulse is off. So for system requirement, we are using a 100 nanosecond pulse, and the pulse repetition frequency is 33 microsecond. So basically we are using here a DD, a double drift impaired diode, that is basically a avalanche transit time device. The structure is taken as P plus P and N plus. So formally, in generally, we first consider some our P-type substrate, then we form a P by using some ion implantation, and then we form N and then N plus region. Okay. So basically here the active area is P and N. Since we are working in the frequencies in 94 gigahertz, so the active area, that is PNN, is nearly 0.7 micron for silicon carbide. So what is the device design methodology? First we are starting from the device physics, starting from Poissons and continuity equation to solve it appropriate boundary condition. Then we obtain DC breakdown voltage, the current and electric field profiles. Then we got the device impedance and circuit impedance, and then we optimize the frequency of operation. So for for two-terminal device like ATD device, the condition for oscillation is that that is not normally that we obtain for four-terminal device. So we need to use the device to mount in an external waveguide circuit from which we can get the condition of oscillation. So here you can see GD and GB is a complex impedance that is obtained from the device, and it is mounted on an waveguide oscillator, and that having also the complex impedance. So for condition for a sustained oscillation, that is the positive conductance of the device should be equal to the positive contra the load, that is the circuit, and the negative susceptance of the device should be equal to the inductive substance of the load. So if it is obtained, then we can get a sustained oscillation in case of ATT device. So here first we are starting from the doping profile, then the electric field, then we are obtaining the GB plot, that is conductance subsidence plot for our design frequency. So here we are using a formula how to predict the active area that is the WNP, that is for P-type or N-type material. It will be written by the empirical formula 0.37 VSN VSP divided by F, where WN is the active area, VSN is the saturated drift velocity per electron and hole, and F is the frequency of operation. So if we consider here 94, so we get nearly the active area as 90.7 micron. So after once we getting this, we are using computer simulation and we are optimizing the width, and then we get the optimum frequency of oscillation. So this is the basically the material parameter that is used for silicon carbide. It is basically 4S silicon carbide we are using, and it's have a band gap energy is 3.43 electron volt, and the temperature at room temperature. This is the parameter used for. You can see the saturated drift velocity is very high. It is 2.12 into 15 meter per second. That is and different. That will be whole. So for silicon carbide, the saturated drift velocity for electron and hole are different. And we obtained the result for DC part, that is the variation of electric field in the depletion region of the ATD device, then the normalized doping profile, and then actual doping profile. Once we obtain, then we get the GB plot, that is how much power we can obtain. That means if we have designed for 94 gigahertz, because why 94? Because it is the system requirement. W-band frequency is used for defense application. It is mainly used in our defense R&D organization. Okay, so we optimize the design for 94 gigahertz, and here we see the bias current is nearly 5.8 into 10 to the power 8 ampere per meter square, and the breakdown voltage is nearly, here we got is 246. You can see the 5 point, that is the 94 gigahertz optimum frequency. Here the J0, that is the bias current density, is 5.1 into 10 to the power 8 ampere per meter square, and whereas the breakdown voltage is 246 or 246. So if we multiply it by the J0, and that means the bias current density with the electric field, we getting the power. Although it is often we got the simulation data is output power is 605. It is the pulse output power, that is, it may be seems that so much power cannot be obtained, but since we are operating in a pulse mode, so we can predict that a high power can be obtained from this one. But the efficiency of the device is nearly 15 to 16. That is very high also for ATD device. For ATD device, most of the power is converted to heat, so the adequate heat arrangement should be there. So once we obtain the design, then we need to consider what should be the design of the device with adequate heat sink arrangement. So we are using here the Yes, this one the heat flux we are generated. That is, if we take the bias current as 5.1 into 10 to the power 8 ampere per meter square, the breakdown voltage and efficiency is nearly 16.6%. That is I already mentioned. Then the heat flux, that means the equivalent heat energy that is generating at the junction, that will be very high. You can see it is 1 into 10 to the 11 watt per meter square. So if there is no adequate energy, heat sink arrangement, so there will be burnout of the device. We cannot get any power, and the device will be burned out. So this is the design. You can see the active area. This is the N layer 0.7, and for P layer it is 0.5, and we have taken a buffer layer of 100 nanometer, and here we are using a vanadium guarding to stick the heat flow in the towards the diamond sink. So here we are using a nickel ohmic contact of 20 nanometer, also titanium, platinum, and gold mixing is taken. Here is also taken 120 nanometer. Then we considering a 150 micron by 150 micron heat sink, so that the heat will be extracted by the heat sink when there will be no pulse. So since the pulse is on for 100 nanosecond and the pulse repetition frequency is 33 microsecond, we have to see whether the pulse heat should be, whatever the temperature that is generated at the junction should be extracted during the pulse all time. Okay. So this is the bias, actually bias current we are giving to the device. Actually is a triangular shape. So here it is 100 nanosecond pulse duration. This is actually obtained from the circuit as well as simulation. The green noise is for that is actually obtained from the circuit. Now we can see that this is the active device. So here heat will be generated. So we are making the pulse of 100 nanosecond duration, and after 100 nanosecond it will be off. So we have to see how much the heat is generated during the pulse on time. So you can see here when the pulse on is 15 nanosecond, the junction temperature rises nearly 600 Kelvin. Okay. Now, when the pulse on duration is 100 nanosecond, so up to 100 nanosecond pulse will be on, so we get a temperature, it is nearly 750 maximum temperature is going. Now the pulse will be off. After 100 nanosecond, pulse will be off. So in that time, although the pulse is off, so when the pulse is 150 nanosecond, that means the time, then heat will be flow from the active area to the diamond heatsink. So it is 150 nanosecond. Then if we go through at 1 microsecond, so you can see that temperature is the junction going to decrease, and within 2 microsecond you see that it is coming to the room temperature. That means since the pulse repetition is 33 microsecond, so within 2 microsecond heat will be extracted. So there will be no chance of the burnout of the device. Okay. Now if we make a comparison that how the junction temperature rises with the bias current as well, that is the heat flux, we will see that at the heat flux increases, the junction temperature will be increases. So for 1 into 10 to the 11 watt per meter, the junction temperature is nearly 752, and it will be increases for 952 for 1.2, and 1.5 it will be nearly 150 Kelvin. Okay. Although the temperature is going to rise when pulse is off, and within 2 microseconds the pulse will be the heat will be extracted from the junction. Now the opposite one, suppose we are making the pulse duration more, the pulse on time maybe suppose 120, 150. So we make a comparative study, that is how the junction temperature changes with the pulse on duration. So if we take there is 3 reasons. Here you can see that the heat flux 1.2, 1.5, and if the pulse on duration is increases from 100 to 150 microsecond, then the junction temperature will rises from nearly it is 850, it is nearly 1000, and here it is nearly 1100. Okay. Now to validate our model, we make a just 1 minute. So within to validate this model, we make a parallel study. That means if we consider the thermal resistance, how it changes with the pulse width, Suppose we are make a comparative study of pulse width with the thermal resistance, and we have seen that for 100 nanosecond pulse width, the thermal resistance is 1.2. And in the next plot, we can see that the pulse thermal resistance, transient thermal resistance, it is 1.2. We are getting the junction temperature is near 742. So in your previous model from the COMSOL thermal modeling, we are getting 756, and now we are getting nearly 742. So it is comparable. So that validates our model. Okay. So if any question from your end, it will be welcome.
Yeah, so you have used, I think, Poisson equation and continuity equation
Yes.
to model this.
This is part of the device.
Yeah, so what is the technique you have used to solve?
Sir, we are using Rangekut method of numerical method.
So far I understand this is the differential equations.
Yes, yes.
These equations are differential equations.
Yes.
And you are using
The MATLAB, sir, MATLAB program this.
You are using here console multiplication.
No, sir, that is about thermal modeling part, not.
Acha.
For thermal modeling, I am using. We are using.
Console multiplication, there is a.
Yes.
There is a method to solve.
No, sir, actually, sir.
Poisson equation as well as.
No, sir, device solving, that means the GB plot, all are taking from the MATLAB programming. Huh? MATLAB programming. We are using MATLAB, not the.
We are using MATLAB. Okay. Okay. And yeah. So you are using heat sink also too.
Yes, sir.
Heat sink.
Yes.
In order to dissipate.
So actually, from the DC part, that means the thermal ring, we only going for the diode. When is mounting the circuit, then we need to accompany that is the heatsink arrangement that will be integrated on the circuit part. So here COMSOL used to find out that how much temperature will be increases when the pulse on time.
Okay. So 94 gigahertz oscillator you are developing.
Yes.
For what application?
Sir, for defense, it is basically used for missile guidance like NAG missile. For Shikar, that means the signal, that means to control the path of a missile.
So oscillator will control the path of the missile.
Yes, to guide it. For low frequency range, it is mainly used for defense in NAG missile. Yes.
Broader area.
Yes.
Okay, thank you. Yeah. Any question from the audience? We are running short of time.
Okay.
Okay, thank you so
much.
Thank you, sir. For coming here. You are from Asansol Engineering College.
Yes, sir.
Okay, so thank you. Welcome again for coming here. And I think next we can move to 105 is going to online presentation, but we have 134. So the paper title, a compact miniaturized implantable antenna for 2.45 gigahertz ISM band application. And the authors of this article is Marantham Santosh Kumar Singh. Most welcome, please come. And others are Saurav Roy, Sumendru Ghosh, and Abhishek Sharkel. And they belong to NIT Meghalaya and North Tripura District Polytechnic College, Dharmanagar, Tripura. So with us we have M. Santosh Kumar Singh. So this
good
is the
evening all.
Second last presentation.
Good evening, respected session chairs. Today I am presenting my work entitled A Compact Miniaturized Implantable Antenna for 2.45 GHz ISM band application. So these are the outlines of today's my presentation. In the introduction, I will discuss about the categories and antennas for medical devices, design challenges, device configuration, simulation environment, and validation. And I will go to my work, a compact miniaturized implantable antenna for 2.45 GHz ISM band. And after that, I will give my conclusion remark. to begin with, as we all know that we are influenced by the development of technology in our day-to-day life. This technological development is also observed in our health sector also. So, with that in our mind, what we comes to do is that the medical devices, which assist in our, which assist in helping in the diagnosis or detection of disease or deformation in our body. In broad sense, these medical devices can be categorized as in-body and off-body, on-body, and based on that, the in-body devices, which includes implantable medical devices and adjustable medical devices. And on the other side, the on-body devices, which are wearable medical devices. What are the purpose of these devices? The purpose of these devices is that to monitor or sensing the physiological parameter of human body. And that will help in a therapeutic purpose or in a remedy. So these devices are influencing in day-to-day life also. So come to the point that why I am coming to the antenna. Before that, the wireless communication technology also is developing in a very rapid rate. So all these medical devices, which are traditionally wired or which is very hectic for doing the operation and changing the device and all those things, this comes to the wireless device. To make that wireless, we need an efficient antenna. So to make that efficient antenna is a key component, which is an integral part of that device. To send the data, maybe from the inside of the body or maybe from the surface of the body to the control unit. So that we require an antenna. But many literatures have reported many different topologies such as spiral structure, serpentine structure, meandering structure. Why these topologies are selected? As we all know that if a device which we are supposed to put on a body, or we have to implant inside our body, that should be very small. So to make the device itself small, there is a relation between the size of the antenna also. So that to reduce the size of the antenna, we have to make that electrically small. So to make an electrically small device, that means we have to change the structure of the device so that their electrical length may be larger, so that the frequency may be reduced. So this spiral, serpentine, whether these topologies are working on different medical bands. This is medical radio band, that is 4012, 406, MICS band 4022, 405, ISM band 902, 948, 2.4 to 2.48, and in the recent time people are also using midfield band, that is 450 to 160, 19240. So these are the reported frequencies which people work with. Related to this, when we are designing antenna, we face many challenges because in a traditional antenna we work on the free space, but when designing antenna, which is particularly dedicated for body centric, we face many. We have to consider those challenges, such as the size restriction, because device must be small, so antenna size automatically that should be reduced. And the choosing of operating frequency. This is a trade-off. This is a trade-off in the sense, if we are choosing high frequency, then size may be reduced. If we are choosing low frequency, that may be low frequency, the size may be high. But in this point, I will be happy to address the one question from the reviewer, why you are choosing 2.45 gigahertz. If I go to my previous slide, these are some of the bands which people are working on. So I am choosing this one, 2.4 to 2.4, which is the largest among these, which is medically dedicated for that. So coming to my list, that trade-off why I am saying is that when we are switching the lower side of the frequency, the size will be increased. That is one problem. If I go towards very higher frequency, which is other than the specified frequency,
Because based on the frequency, the body tissues are very loose. If we go towards a higher frequency, then there will be attenuation. Because of that attenuation, even we can't go beyond that, which is indicated. That's why I choose my 2.45 gigahertz, which is common and which is also prescribed, for medical devices. That's why I choose this 2.4 to 2.49. I think this addresses the first question of the reviewer. And so another one is dielectric properties of tissue. Our tissues are very highly conductive. Very highly conductive. So why I am putting here as a challenge? Highly conductive means our device antenna itself is a metallic structure. If we are putting a current flowing structure inside a conductive area, there will be high chance of short circuiting. That means a failure of the device. Then we have to consider when designing. For that, what we consider biocompatibility. Because antenna, the device which included antenna are foreign body to our body. They are foreign body to our body. So we have to make them comfortable with our body. To make that, what we use is a superstrate or insulation. And that is also a point which we have to consider. And the low power requirement, there is most of the devices are battery powered. So we have to design the device such that their consumption of power is very less, so that the lifespan of the device will be longer. And specific absorption rate, whenever our tissue is exposed to electromagnetic field, some amount of energy is absorbed by our tissue, which can cause our heat up of the cell. Heat up of the cell in the sense if it reaches a limit, then the cell will be dying. That also we have to preserve. To preserve that one IEEE standard I have in a reference. The IEEE have restricted us to 1.6 watt per kg for 1 gram average and 2 watt per kg for 10 gram average. And the bandwidth requirement. Yes, we know that body, when we are loading an antenna to the body itself has a property. There is a possibility of detuning of the frequency. So if our bandwidth is high, then it can cover the frequency range. So coming to our design, before coming to the design, these are the preconditions. What we consider the device configuration. We can't put antenna alone inside our body. This should be a compact device package. So it is a holistic way to design the antenna, and it should be in the simulation stage or in the validation stage. We have to include the whole other component. Based on the literature, the device components are represented by dielectric material or PEC material. So for battery, we use PEC material, and these are the dielectric materials, which can replace the electronic circuitry, which is mostly PCB or those things, including antenna. This is device configuration, which I consider in my work. So simulation environment. To accelerate our work, first
half time is over. Then half time is over.
Then it's 5 minutes.
Yeah.
Okay, I will complete it. Thank you, sir. So simulation, we have to perform the simulation in a different issue level. So for acceleration of the results, we used to do on the homogeneous phantom, which comprises of maybe skin, maybe muscle, or maybe bone, based on the application. And another one is that our human body is different tissue level. So we can use multi-level as skin, fat, muscle. This is the simulation environment. So this is the implantable scenario which is put inside the tissue, and this is device wearable scenario which is put outside of the simulation skin. So the next thing is the invalidation. Validation. How we will do the validation of those results which are obtained in the simulation? We can validate those results through in vitro measurement inside the animal meat. This is with reference to the many literatures are there. Out of that, I took the relevant is 6 and 7. Use pork meat. Pork meat because in an equilibrium state, our body homogeneous skin tissue property is equivalent with the pork meat. So we use the one. If not, then we chemically make imaging gel coordinate issue, but this is the problem when we are making multiple frequency mimicking gel. It's hard to get there. So coming to my work, comparing miniature implantable antenna to 2.45 gigahertz ISMN, this is the structure which I designed, and here I have a circular cell. Why I am taking a circular cell is that to reduce the invasiveness of the structure in the body. That's why I took the circular structure. Here I am taking superstrate and the substrate as a dynamic measure that is of 10.2 permittivity. And these are the geometrical parameters which I optimize. And in developing that design, I gone through many developmental stages. First, I took the
Please show the results.
first I took the circular shape, then to increase the electrical line, and I took the slope. So from this figure, the stage 1, the antenna is resonating somewhere at 5.09 gigahertz, but the matching level is very poor. So to increase, to miniaturize the frequency, I introduce a slot on the beds, and how this slot reduce the frequency, that is miniature, because it increases effective reactance of the structure, so it reduces. But our design target is 2.45 gigahertz, so we more extend the slot length, and it works here in 2.45 gigahertz range. And this can be understood from our impedance graph, where the matching is 50 ohm line, matching is not match here, not match here, and this. This is my simulation level, but from here again, from the surface current distribution, we can understand that the current C, this is the current one. This is ascending. So in the ground side, the current one is ascending.
On which platform you have simulated? On which platform you have simulated?
Sir, it is ANSYS electronic control. And then before it was SLSS. So this is the surface current. This is the gain which I obtained around minus 27.5. In traditional free space antenna, minus 27 is meaningless, very poor or that. But in implantable scenario, more of the literature which I have read, we have studied is from around minus 19 to minus 44 like that. It is considerable range. And from this 3D pattern, we understand, we can see that it is targeting out of body. So it is. So that point, with the safety point, when I separate with one input, the SAR value which obtained is 402.72. This means that if I give an input of 4 milliwatt, then I can maintain the safety regulation for 1 gram. Yes, this is for 10 gram 67.0. That means if I give 29.6 milliwatt, then it satisfies the safety regulation, which is defined by IEEE. So this much result I can say that I can claim that our antenna is well designed, but my validation that should be through my fabrication. Another one question was also raised by our reviewer that you are only presenting the simulated result at the first stage of my submission, but now I fabricated our prototype and I checked the results. Even the result graph I will show. But this is the antenna measurement environment. These are my prototype, and these are the components. This is battery mix replace. These are the dielectric mix. This is my prototype, and this after this, the result which I got in the simulation and the measurement is good consistent, and it covers the ISM band of 2.4 to 2.48. Now I can say that I can conclude that my design is working in 2.45 gigahertz ISM band, and it exhibits a compact size of 16.53 mm3, and which operates in the. And some of my future aspect is that multi-band operation implantable antenna or polarization independent antenna. These are my futures. These are some of the reference which I feel that it is more relevant to my work. Thank you. And if you have
Thank you, Santosh, for your nice and comprehensive presentation and for your good work also. So session is open for inviting question.
yes, sir. Yes, sir. Yeah, yeah. What's your this one? Yeah, this is minus 27.
Yeah, the thing is that, see, because any antenna kind of structure you will get some sort of radiation. So the thing is that there is a getting considerable amount of gain on one. So that thing should be tested. But the result which is being there is showing very 25 degree minus 25.
Yes, sir.
And inspection is also very difficult. Very difficult. Now, have you simulated your structure without the tissue, whatever the tissue you have artificially designed? So, without that environment,
Yes.
how it is behaving in this space? How much gain you are getting?
Oh, that one, sir, I didn't go there because why I am saying that. Your point I get it. I got it.
Because if in this space, if you are getting considerable amount of gain, then only you can say that your antenna is acting properly.
Yes.
There also you are getting gain in minus, say minus 1 degree, minus.
Sir, I was asking, sir, I would
Then you
like
have
to
to change your structure. Because that is not radiating properly. Because here I can see that gain is not considerable.
yeah, in implantable or implantable scenario, most of the gain is obtained there is. But in my design stage, that's what you are saying. I understand that in the next of my work, I will go on that way also. But here,
You get that confidence that this is
yes, sir.
properly.
Yeah. But here, sir, sorry for that. This design structure, if we consider the governing equations of the microstrip antenna or all those things, this is a diameter of 9 mm. But if we are considering diameter of 9 mm, then it will give around 15, 16 gigahertz. But at that time, what I consider is that the dielectric property which we are supposed to load on that environment, that is, I took this for 2.45 gigahertz, that is 38 per dBdt, and 0.6 Siemens per meter. If I give that effective wavelength, then it comes to around 9.002, something like that. So based on that, I think this design I will. But sir, what you are suggesting me, like that, I will work that. But I will try to improve that on my.
And the 34 directly you are talking.
No, that's 40.
38. That is for tissue.
That is it. At this particular frequency. That means it is tissue dependent, frequency dependent. Tissue properties.
You have some structure where this is loaded with some battery.
Yeah. That means our analysis process. Component.
How the generating alternating signal over there?
Solution?
How the generating 2.4 gigahertz signal over here?
2.4
gigahertz.
So this is a schematic diagram representation, but in my design I put 50 ohms.
Not talking because you are going to feed the signal to the antenna.
Yes.
Get the radiation of it.
Yes.
So how are you going to do that? Because your battery is not going to give you.
No, these are dummies. Dummy in the sense when we are simulating, we have to give those properties. But this battery has the property of PEC.
Even environment.
Yes, we have to pick that environment. That environment that is dummy, but it has a property of PEC. That is perfect electric.
That's true.
Yes.
Even proper environment.
Yes.
Okay, any more question? So let us give big hand to him for his nice work. Thank you for coming and presenting your work. So I think we can move next. One online presentation is there, I think. Is ready? Uh-huh. Is available or not? 105. The title is an ultra-thin multifunctional polarization converting meta surface with wide angular stability. And authors are Somendu Ghosh, Saurabh Roy, M. Santosh Kumar Singh, and Abhishek Sharkel. So, Somendu Ghosh, it seems, has to project. Is that
Yes, sir, I'm
correct?
present. Yes, sir.
Yeah. Sorry?
Share your screen.
Yeah, please share your screen.
Yes, sir, I'm sharing. Is it visible, sir?
We are looking into it. Hold on.
Is it visible, sir?
Not yet. Not yet. Yeah, now it is visible.
Okay, thank you, sir. Good evening to all. I'm Somendu Ghosh. I'm an ultra-thin multifunctional with wide angular stability.
Somendu Ghosh,
Yes, sir.
you have been given 10 minutes.
Yeah.
Please be brief and concentrate on your results in this presentation.
Okay,
This is
sir.
your last presentation of this session. Over
Okay,
to
sir.
you.
In the beginning of our work, is the brief outline of our paper. Firstly, there is an introduction part. I'm discussing the word about metabit radiation. Then I'll go to the what is the polarization and their different states. After that, what is the polarization converter and polarization converter, and after that, I will show some recent relevant work in the domain of polarization converter. And then uh, with that limitation, we'll present our work on an ultra-thin multifunctional converting meta surface with wide angle. Then we'll see award in the conclusion. Initially, what's the metabit? It starts with a structure uh, which has significant application with wide range of application. And nowadays, the 2D counterpart of the metal material is gaining popularity due to several applications like laser harvesting, absorption, polarization formation. And what is first before going to polarization formation? What is polarization? We know that polarization is a non-invariant right? And it's very sensitive parameter and normally divided by three categories. First, linear polarization. Linear polarization means it can be divided either bipolarized linear polarization and mixed polarized linear polarization. And then circular polarization and another term elliptical polarization. So after the polarization and their states, I'm going to polarization converter. Polarization converter is basically device which can convert linearly polarized waves like cross-polarized emission, polarized emission, bipolarized emission, or vice versa, or for linearly polarized, bipolarly polarized. And during that conversion, um, reflective or transmissive polarization. In that slide, you can see that uh, the reflective type polarization converting basically convert the incident wave into reflection in transmission. Polarization converter convert to the transmission.
And reflective type polarization converter is mainly dependent on co and cross polarization reflection, but transmitting type is dependent on both the reflection as well as the transmitting polarization. This is some reported work on polarization conversion. Firstly, a strip and ring topology is proposed by an author for dual band linear polarization conversion. And later on, more recently, an alternative converter is proposed using an open step converter. And after the linear to linear polarization, there are some proposed conversion called linear to circular polarization conversion. That the only usual converter is proposed for single band linear to circular polarization conversion, and later on, dual band linear to circular polarization conversion is proposed based on the square ring and split ring case. But in that linear to circular polarization conversion, their band is very limited, and either there is many of the polarization converter. Either they are focused on the either linear to linear polarization conversion or linear to circular polarization conversion. Very few works developed in the domain of multifunctional polarization conversion. You can simultaneously convert linear to linear polarization conversion as well as linear to circular polarization conversion. Here, we have proposed the method of linear to circular simultaneous multifunctional polarization conversion. The meta surface is based on the uh, unique fence shape structure, a thin substrate, ultra thin substrate of 1.4 mm. And we have simulated using the clockwise port excitation and what the result that you can see in that region of 6.2 to 6.5 ICCDEC 6.18 to 9 gigahertz frequency. The co-polarized reflection is 10 hertz, but the cross-polarization reflection is 8 hertz. And here the RY polarized reflection and cross-polarized reflection indicates the bipolarized incident wave started in the polarized reflection af- after the metasurface. In that frequency range of 6.2 to 6.6 gigahertz frequency and 6.7 and 10.52 gigahertz, the both the co and cross polarization reflection is almost equal. 90-degree phase difference between the reflection phase is observed. Which satisfy the criteria for linear to circular polarization, where the two polarized reflection is almost equal with 90. The linear to linear polarization is specified by the polarization conversion decision by the governing equation. Here in that governing equation, uh, only the reflection performance matters, and that in the governing equation, the meta surface shows highly efficient linear to linear polarization conversion at that 6.56 and 9.18 to 9.82 gigahertz frequency band. And the linear to circular polarization conversion can be estimated by the axial ratio. Here the governing equation shows the linear to circular polarization conversion. The axial ratio shows that linear to circular polarization conversion or the band of 6.0 to 6.17 gigahertz, 6.71 to 8.93 gigahertz, and 10.03 to 10.52 gigahertz. And with that calculated polarization conversion and axial ratio performance, we can say that this polarization converter can act as a multifunction polarization converter because it simultaneously converts linear to linear polarization as well as linear to circular polarization based on the polarization conversion ratio and axial ratio performance. And another interesting thing is angular stability. Angular stability is very much required for many practical applications where incidence angle changes. In our metasurface, the metasurface shows almost stable response up to 45 degree of angle of incidence, and it doesn't changes its response up to 30 degree of incidence angle. The PCR response shows in the 60 degree also the PCR response doesn't changes much in the lower frequency band, and in the linear to circular polarization the axial ratio doesn't changes much in the lower frequency, but higher frequency some degradation occurs. Here is the surface current distribution. The surface current distribution is observed for linear for explaining the linear to linear polarization conversion. Here the opposite surface current distribution at the two resonance frequency at 6.4 and 9.5 GHz indicates the magnetic dipole resonance for linear to linear polarization conversion, which enhances the magnetic permeability and polarization linear to linear polarization conversion occur. And using the theoretical analysis to understand the theoretical, when we decompose the incident electric field U and V axis, U and V axis is the plus minus 45 degree is the X and Y axis, which shows nearly equal operating, nearly equal, because it is the co-polarized reflection on the U and V axis, and due to the symmetry of the structure on the basis of U and V axis, which are 45 degree inclined. Here the phase difference between the U and V reflection phase is the prime factor. For linear to circular polarization case, 90 degree phase difference is observed in that frequency range of 6.0 to 6.17, 6.712 to 8.93 and 10.03 to 10.52. But 180 degree phase difference is observed for linear to linear polarization conversion, where in that frequency range of 6.27 to 6.56 and 9.18 to 9.8 GHz. And we can come to that we have proposed an ultra thin metasurface, and with that ultra thin we can easily mount in a surface where polarization conversion is required, and it converts the dual band of linear to linear polarization and triple band of linear to circular polarization conversion. It shows it depicts the 45 degree angular stability, and several practical applications like radar cross section reduction, multipolarization communication devices require this polarization converter metasurface. We can reduce the radar cross section for several defense applications. Also, the multipolarized antenna, the multipolarization state of an antenna can be achieved by use that metasurface on the top of the devices. These some references. Thank you. Sir, any question?
We have done good job. So, thank you. Session is open for questions. One or two questions we can take. If I do not know how far. Okay, so let us thanks to Somendu Ghosh. I think we are running short of time also. This is the last paper, and I would like to thanks to all participants, all audience who are here with us. And I thanks to my colleague also here. Sitting alone, it would have been difficult. Dr. Swarnajyoti Patra, as well as organizing committee for giving me this opportunity uh, to chair this session. I really enjoyed. Lot of research work researchers have come up and they have shared among us. So with this, I would like to hand over this session to organizing committee members. Thank you so much.
Now we have come to the end of this technical session 2. Thank you so much to all the presenters for sharing their valuable knowledge and brilliant ideas among us. This will surely encourage us in our future. And best wishes to all the presenters for your future. Thank you so much to both of our chairmen, Dr. S.C. Arya sir and Dr. Swarnajyoti Patra sir for the honor. Now I would like to request Professor Rupaban Subadar sir to felicitate Professor S.C. Arya sir. Sir.
I'm so glad to get input from you, sir. Thank you so much.
Now I request Dr. Raskishore Mudoy sir to felicitate Dr. Swarnajyoti Patra sir. Thank you, sir. Thank you so much, everyone, for your cooperation. Have a good evening.